And this is Nate Hall, he's a seagrass guy, that's all you need to know. If there's anything else they need to know, Joel can tell them.
That's it. I was going to say, because the first thing I want to tell you is I'm not a seagrass guy, really.
Well, that's what you said, well, you're a seagrass guy today.
Yeah, I'm a seagrass guy today. Exactly.
And I do want to say this. Nate knows more about a lot than anybody I know.
And you told me that.
And you go to any like creek, bayou, sound, bay, river.
Bathtub.
Yeah, Nate holds the back hurricane in Chesapeake Bay in 1972. Well, you just might say, what was the hurricane somewhere and what year? And this guy knows it. He knows a ton about a lot of stuff. So that's my comment.
All right, Nate, it's yours.
So I'll start back where I left off. I'm not really a seagrass person. But I'm interested in seagrass. I see that they're super important. I'm a water quality person, really. And particularly I study algal blooms, algae eutrophication, affects aquatic systems, stuff like that. So that's how I got into the seagrass thing, because there's a really strong connection. You'll see some of that. So the title is Why We're Worried About Our Submerged Aquatic Vegetation and what we're going to do about it, or what we are doing about it. And I just want to mention, this is a partnership, really, with a lot of different groups. The Albemarle Pamlico National Estuary Partnership factors into this a lot. This is part of the National Estuary program, so it's an EPA-run program. So ABNEPS also falls somehow under Department of Environmental Quality.
Half a step that way.
So that you can say,
Perfect.
right.
She's already sent you to the corner, you barely knew it.
And then us from UNC Marine Sciences and a big partner at UNC Swimming, Jesse Jarvis's group. So this is a Google Earth tour. All of this dark stuff here, that is seagrass. And I'm going a little fast, but still, all this is seagrass. Here I'm stopping in this little spot. There's a seagrass patch there. These inlets have changed a lot. That's something I'll show you a little bit later. But basically this whole area right behind Outer Banks, so like the first few hundred meters to a half a mile out, maybe sometimes like even a mile out, is seagrass beds. We have about 100,000 acres, and then even going into some of the low salinity estuaries, we have different types of submerged aquatic vegetation that have these low salinity areas. So that's the mouth valley of the river. You can see that's Ballston area, wild celery, really good duckweed. And then going up into the North River. Anyway, just throughout North Carolina's estuaries, in the salty area behind Outer Banks, and then going up into our low salinity estuaries, we have different types of submerged aquatic vegetation. We have the seagrasses in the really salty areas, and then all kinds of low salinity submerged aquatic vegetation. Now I'm zooming in on a particular seagrass bed that's right off the Hers Island Bridge Causeway.
Better known as the old bridge.
So now we're going to go underwater. Start thinking about, why is the seagrass even important? Why do we care? Hopefully this doesn't make everybody sick. I'm not a videographer by any means. But I made this yesterday. I asked Joel for a video, and he gave me a really nice video that had no fish in it. So I made sure there was going to be some fish. I don't know, the crab, the blue crab.
Are the black things bidium?
That's what I was going to ask you. I don't know. Is that what it is? What is bidium?
Bidium's a little tiny itty bitty snail.
Okay. Itty bitty bidium.
Yeah.
That's a hermit crab. You barely see its little claw in there. And there are fish. There they are. And they're swarming because that's
Kind of murky, is that?
it was kind of murky, and also it stirred up a little bit. And just like haze on the camera face too that kind of showed up while I was doing it. I didn't realize it was after I was done. I was chunking little pieces of oyster meat into the water, chumming the water, and kingfish. And you can see this, that's what that is right there. In a second, you'll see it like dart off. Even if you don't see the fish carrying it, you'll see that the deck goes. So there's a lot of fish that live in these seagrass beds. Not just fish, crabs, all kinds of stuff. see enough there. Move on.
This is good.
Yeah, if there be a chance. My daughters love just going out with a mask and just snorkeling, but not even moving, just laying there and watching the stuff swim by underneath it. Especially the seagrass beds out on the backside of Core Banks. Water's a little bit deeper and is this still? I moved on right now.
This is
Right. Okay, now I'm moving. This is the part where it's going to make you sick. I saw a little puff of sediment right there. It was a little dirty spot.
Yeah.
I knew there was something there, and that was that crab. Came out of the hole. Blue crabs. Marshes are, salt seagrass habitats are super important for juvenile blue crabs. The denser the seagrass is, the better it is for the survival of juvenile blue crabs. There's been a couple studies that show that. This is where really moving through the seagrass fast.
I was in Boomtown yesterday and there was a big fish hunting those little fish. And I could see it from a stand-up paddleboard.
Yeah,
It was shaped like a trout.
could have been.
Red drum.
Yeah, or a drum. Yeah.
It was kind of long
Little
and
hermit crab.
torpedo shaped,
Yeah.
chasing the little fish. A bunch of them.
Yep. Well, there's definitely all kinds of predators that hang out in seagrass as well. As all the juvenile fish hiding from the predators.
Yeah, I saw a small stingray this morning. I went
Yeah,
back.
that was it. Like I said, not the videographer. These are pictures that Joel's group has taken over how long? 10 years, 12 years, 15? So this gives an idea of the type of diversity of fish. I don't know how many are in here, different species, but there's at least probably 20 or 30 just showing this picture, including some really neat ones. Like mangrove snappers or gray snappers here, telling from line. Gag groupers,
Who's this guy with the teeth?
Cabera snapper maybe? Where?
Second one down, second
Here?
one. Over one. It looks like it's teeth.
This.
Yes.
That is a little parasitic amphipod, isopod, that is, was it crawling out of the mouth of that silverperch?
Yeah. There are parasites that will go in and bite the tongue of a fish, and the tongue dissolves away, and then it's just the parasite that's like the tongue.
Sorry.
Yeah.
And I think that's a silver perch.
Yeah, I remember, that's what it looks like to me, that's what I'm saying that. So one of Joel's students has done evaluation of seagrass habitat as for how many dollars per year does an acre of seagrass produce as far as like fisheries enhancement.
Amazing.
And it works out, it's about, $750 per hectare. A hectare is about 2.5 acres, so it's $300 an acre or something like that. And if you add up the 90,000 acres that we have, it's about $27 billion per year of fisheries enhancement. So seagrass matters monetarily for our commercial fisheries. And seagrass gets used more than other habitats. So this was a study that Joel's also a part of, where they compare the fish utilization of these different habitat types, mudflats, seagrass. And all seagrass is created equally. You have seagrass next to something else that's really interesting to fish, like salt marsh. So something like here, we have seagrass adjacent to a salt marsh, or maybe next to an oyster reef, you can get more fish utilization than if it was just seagrass by itself. Still, seagrass is obviously really important for fish. And I put this up here to remind myself that it's not just about fish, because ducks are important. This big cloud of redheads coming in the background here, that duck blind, it's coming in because the seagrass that's out there in Core Banks. And we get tens of thousands of redheads in a good year that come visit us, partially for seagrass. Now corn is a big thing too, I think. But yeah, so it's not just, and seagrass also, it stores carbon. It prevents shoreline erosion. There's a lot of different reasons why seagrass is important, not just fish. One of the things about seagrass, and all the SAB for that matter, they need high light. I say seagrass needs about 20% of incoming sunlight if it's going to do well. And the reason why it needs so much is because it's got roots that go down into sediments that don't have any oxygen. So to keep those roots healthy, it has to pump oxygen to the roots. And what it's fighting against is hydrogen sulfide. About 8% of the salts in seawater are sulfate. And the bacteria quickly run out of oxygen when they're consuming that organic matter deposited in sediments. They run out of oxygen probably in the first millimeter, maybe centimeter, but it's really quick. But there's still tons of sulfate that's diffusing in from seawater. And so other types of bacteria then can use the sulfate, break down organic matter, but in the process it produces hydrogen sulfide, which is toxic. If that hydrogen sulfide makes its way into the roots and into the seagrass, it'll kill the seagrass.
How deep do the roots go?
Like that? Yeah, so they go way down into what otherwise would be completely anoxic sediments. And the only way they can survive is by pumping oxygen down into the root tissues. So if they're not doing a lot of photosynthesis, then they're not pumping oxygen down, and the plants often die from the bottom up. So you can have what looks healthy on top, and you pull the top off and you get roots because the roots have died. Yeah. So they need lots of light for that reason, and that's to detoxify their surroundings. And then out there in the water, there's three things mainly that reduce the amount of light that gets to the bottom. Depth is obviously the first one. If it's really deep water, you're going to have less light at the bottom. But depth being constant, phytoplankton or the microalgae that drift around in the water, they absorb light. Suspended sediments absorb light, and then color dissolved organic matter. The acronym is for that CDOM. It's a lot easier to say than the other. It's that tea-colored stuff. You've seen it coming out of swamps, creeks. Some of the waters around here are really darkly stained. Like Trent River, for example, is a really darkly stained creek or river. It comes out of swamps.
Is that from like tannins?
Yes, it's tannins, exactly. And it's tea-colored. That's what that is too. So we measure these different ways. For phytoplankton, we typically measure the amount of phytoplankton in the water by the pigment that they contain. So all plants contain chlorophyll A. That's the main light-absorbing pigment. And then for sediments, we use a turbidometer, measuring turbidity. It's usually in units of something called nephelometric turbidity units.
What is turbidity?
Turbidity, it literally is just the scattering of light by
Okay.
particles. But the main thing that scatters light is usually suspended sediments.
Okay.
Yeah. And then this color, we just measure that by how much, if you filter all the particles out, how much light gets absorbed just by that dissolved stuff in the water itself. So that's how I measure it. Those are the three things. And because phytoplankton are one of the big three things that absorb light, eutrophication, or the overproduction of microalgal biomass in the water, that's there. It's bad for seagrasses. The more phytoplankton you have in the water, the more shading you have, decreases light penetration, but it also increases the amount of organic matter deposited in the sediments, which then fuels the production of the hydrogen sulfide that's so toxic. So it makes the hydrogen sulfide worse, but it also cuts the light that they would need to deal with hydrogen sulfide in sediments. And then to make it worse, if you have a lot of organic matter, you can run into situations where you have less oxygen up in the water column. So then, it just compounds the impacts of the reduction of light. So generally, you can go from the situation where you have a lot of seagrass, and then if you just keep dumping nutrients and get more and more phytoplankton, you can reach a point, like a tipping point, where you switch completely to a phytoplankton-dominated state, which the phytoplankton are always going to win in competition for light. They only need about 1% of incident radius. plants to grow, and the seagrass need about 20%. So if there's ever just competition for light, the phytoplankton are going to win. So you can get this tipping point reach where you have tons of phytoplankton, no seagrass, and it's really hard to get back. And that's the kind of situation we definitely don't want to see. I'll show you an example of it that's happened. So eutrophication is one of the stresses that our seagrass beds are under, but also storms are another stress. This is a picture of North Core Banks after Hurricane Dorian in 2019. You see all these little, these are all new inlets that were cut. And in the process, there was a lot of seagrass that was just scoured. Just physically rolled up and removed during some of the storms. The long-term impacts of this is something that Joel's been looking at, and your take on it, short-term, yes, long-term, this probably isn't that big of a deal, or no?
Unclear.
Unclear. Okay.
Are you gonna talk about the patchiness that heads out?
Yeah. That'll show up in some. The other thing is the effects of sea level rise. I said water depth is the biggest, for sure. If you have deeper water, you're gonna have less light. I mean, with all the clarity being equal. So we're getting more water as sea level rises, and we really don't understand how that's affecting light availability of seagrasses. Because we know the water's probably getting deeper over some of these beds, but it may be getting clear. I mean, our Beaufort Inlet has widened 3/4 of a mile in the last 10 years.
Recently.
Or less than 10 years. So we may be getting generally clear ocean water, having more of an influence in the estuary. And if that's the case, maybe water's getting clearer, possibly. Maybe it's some kind of balance. This is another thing that Joel's browsing on his students. The same one that did study on fish, the evaluation of seagrasses for fish production. And then there's warming. We're at this weird place along the East Coast where we have a northern species at its southern range, that's the Zoster marina, and then a southern species that's northern range. So we're at this biogeographic breakpoint where these two species coexist. The northern one, as things get warmer, it may not do well under these warming waters. And there's some good evidence, not so much that we're getting on average warmer, but the number of warm or hot days is increasing. And that's what a study from Amy Bartenfelder a few years ago showed, was that, and this was done right here in Back Sound. So it's local data showing that the length of days above 25 degrees Celsius has increased a lot since 1960? We see it's going up by 50 days. Yeah. So, maybe the average temperatures aren't more than a degree or so warmer, but the number of days of really warm water has gone up a lot, and that can lead to shifts in distribution. We really don't understand if that's happening yet, and I don't think we understand what the consequences of that would be. I know there's some ideas, but, and correct if I'm wrong, Joel, yeah.
If you, can you look at those two grasses and you quickly go, which one's which one?
I could do it, and I'd probably be wrong, Joel can do it.
So, sorry, Nate.
No,
So, south of us, there's a species called turtle grass. Guess what likes to eat turtle grass?
Turtles.
There's a species of manatee grass. Guess what likes to eat manatee grass? Nate was about ducks, so you probably should have mentioned widgeon grass. Guess what likes to eat widgeon grass? Beautiful ducks.
Yeah.
And then the one that's Zostra is eelgrass. And guess what likes to eat eelgrass? No, I don't know why it's called eelgrass. But so eelgrass, to land the plane, eelgrass, someone told me, is like fettuccine noodles. It's flat. And halibut or shoalgrass is like angel hair pasta. It's all, to me, it looks like upside down pine straw. And then this widgeon grass is really thin, but it has multiple branches. So if you see lots of branches, it's probably the one that widgeon and other ducks like.
Yeah, and that was, the widgeon grass is not even on here. But,
And it's just kind of, it just comes and goes. It has,
yeah.
it's like the crazy grass. It just pops up.
And it can go from like full strength salinity all the way to freshwater too. So that's, whereas these two are restricted to, you know, pretty salty water, like at least half strength salinity. So yeah, this is another, we're worried about this. I don't think we have answers about exactly how it's going to affect things yet. But we're definitely worried about it. So that's kind of what we're, the stresses that are out there, how it's actually impacting submerged aquatic vegetation in North Carolina. Yeah, we're still trying to figure out, but one of the ways we're looking at it are aerial surveys conducted by the Albemarle-Pamlico National Weather Survey Partnership. So they've done 3 of these now, where they flew the whole coast with airplanes and collected tons of images. And then one guy in particular sat down and looked through these images and figured out that's seagrass, that's not, and put this, and it took a long time. But through that effort, we have pretty good records of where the high salinity seagrasses exist. We only have really, it's 3 snapshots. It's like 2006, 2013, and then 2020. And this report from data in 2020 just came out like a week ago because it takes that long. And they're trying to automate it now using some AI stuff. But well, the patterns that emerge, I mean, if we look, let's just look at 2006 and 7 versus 2020. Look at all this dark green. This is the continuous meadows. And a lot of that now is converted to this light green, which is the patchy meadows.
It'd be interesting to do an overview of what economic development is in these areas, like the more houses and things were being built, if that made an impact on that stuff.
Yeah, no, I agree. I don't think any of us have, none of us know the answers to why this transition between continuous to patchy is occurring. But there are lots of things going on, like I just showed you. It's getting warmer. We've had a lot of storms between 2006 and 2020. We don't have a lot of water quality data to see whether or not clarity's changing. That's one of the things we're trying to correct. I'll get that towards the end. People ask me like, okay, has water clarity decreased up here? Guess what? We do not have data on clarity up there. We have a little bit down here, in the southern part down there, sound, but yeah.
If it goes from the darker to the more the patchy, the population of fish and creatures is diminishing as well.
Joel's looking at that. You've been looking at that for how long now? Man.
So I get very frustrated by this because I can't tell anybody that if we lose half the grass, we'll lose half the fish. It's possible the fish would just pile into the remaining. That's possible. But it's certainly correlated with things like these declines in blue crabs, because you talk about blue crabs. It's like, why are blue crabs declining? The management has gotten stricter and stricter and stricter as they have to, but blue crabs haven't been coming back. Is this part of that?
Yeah. And there's some studies that have shown that the patch size correlates with the juvenile blue crab survival. So there's a mechanism there. It's been demonstrated.
And I know we lose some species we believe we lose some species when it converts to patchy. So some species don't care. And then a lot of the camouflage, think of any fish that's camouflaged. They don't like a patchy meadow because they don't want to have to probably jump from patch to patch. I guess blue crabs would be that way. They're a camouflaged species.
Wouldn't the National Seashore be a baseline to compare against, since it doesn't have development?
All right, good.
The impact looks like it's as big on the non-industrial.
This final number down here is the total. This is the total percentage over between this survey and that survey. So we've lost 10% in about 15 years for this north area. And those trends, I mean, it's pretty much all, whoops, was that the wrong arrow? Oh, yeah, wrong arrow key. This is just going down the coast, and it's the same kind of trends. I mean, we're seeing transition between continuous to patchy a lot more light green, a lot less dark green. Here we also saw, look at this in the inlets here, like around Oak Cook Inlet and Hatteras Inlet. There were big areas that were gone after Hurricane Dorian. It really wiped out. And a lot of that was, I think, physically scouring. You know, we had a 7-foot surge that came over Oak Cook Island and North Core Banks after Dorian, and it wreaked havoc on everything out there.
On this particular stretch, they had Seiche, which was the water backed up
That's
on the sound side.
That's it, and then it came back across.
Yeah.
So that's what, yeah.
With spilling everything back out to the ocean.
Yeah, that's what I referred to as
Seiche.
yeah, it was the water initially from the storm pushed everything to the west side of Pamlico Sound, and then when Dorian passed, the wind then pushed all that water right back across, and in Ocracoke, they saw 7 feet of water in 30 minutes. So people were like, scrambling, going up into their attics and stuff, trying to get away from the water that's coming in so fast. That's really scary. But here, 28% in the central zone, a lot of that being associated with these inlets, but still, quite a bit of loss. And it's worrying. And then in the southern zone here in Bogue Sound, this area here, we were really worried about because in the, this is very survey too. So here to here, there was some loss in the western part of Bogue Sound. Now we made it back up though. So there's some good news for that western part of the sound, but overall there's still a loss. Over the 15 years, about 18%. So we're losing about 1% per year of our tosylane seagrasses. And there's this big transition between continuous meadows to patchy that we don't really fully understand the consequences of yet. So it's worrying. We're not in North Carolina anymore. We're in Florida now. The Indian River Lagoon used to have about as much seagrass as we do. And things they had been having some water quality issues. They started losing seagrass, and then they started doing some restoration work, and it was looking good. Up until about 2012, when they had massive algal bloom problems. 2 different species of phytoplankton that are notorious for sucking up light. These are tiny, tiny, tiny little algae that just do a tremendous job of absorbing light. And so it really shaved out a lot of seagrasses, and in a couple of years, they lost about half their seagrass. And things have not improved, as far as I know. The last reports I've seen, still bad. This is one of the situations. There were decades and decades of sewage inputs in the Indian River Lagoon, out of the pipe. And they started bringing those down. They started reducing those, and they thought they were doing good. But they had 300,000 septic tanks around the Indian River Lagoon too that were continuously leaching nutrients. And it seems like at some point there was that tipping point reached. And that it's gone to the situation where it's going to be, hopefully they'll get their seagrasses back, but their bloom problem is still there. We don't want to do this here though. And that's one of the things I'm worried about is Highway 42 coming in. I look at Indian River Lagoon, it's about 2 or 3 meters deep. It's lagoonal, it doesn't flush very much with the tides, and I think, that's Core Sound. That's exactly, you just described Core Sound, except for we don't have 300,000 septic tanks.
Yeah.
It's probably 5,000. And I'd say maybe out of the 5,000, maybe a half of them work. The rest of them might as well just be straight pipes. We're low, and the sea level's coming up, and now we're going to bring more people down here. Yeah.
Sorry, so aside from, septic tanks, leaching and things like that, is this area vulnerable to algal blooms from because it's shallow water, heating, temperature,
Yeah, sure.
rising
It's shallow.
temperatures?
Yeah.
Has there ever been anything like that before that's impacted? I guess I'm just curious, with algal blooms.
The perfect recipe for an algal bloom is a shallow body of water that doesn't move. Reflecting
Oh,
Yeah.
but
I mean,
are there
if you have a shallow water body
Yeah.
that doesn't get flushed and you put nutrients in it, you're gonna grow, for sure. I mean, yeah.
Did your cohorts see that coming when they did the reflecting pool?
No,
Set
I
back
saw
in
the
much.
sample the day after. Yeah, there was a sample that got sent down by the Atlantic. I looked at it with Hans Pearl, recently retired, the day after all the hoopla in the news. It was kind of exciting to see. I still got the samples from the reflecting pool in the office.
Oh, yeah.
Is it
Um,
fixable?
Yeah, I mean, sure, you can fix. I mean, it's a small body of water. It's a lot smaller than any river lagoon
Yeah.
or sound.
Like, well,
Those are hard to
continuous
fix. We can fix the reflecting pool. It might cost a lot of money, but
I read something that said that the green, environmentally responsible paint that they used was actually a biofood for the algae,
I don't want to.
Where? On
reflecting pond.
I thought it was blue.
Yeah, but it's labeled a green product, environmentally
Maybe.
responsible product.
I have no idea. Anyway, this is what we don't want to see happen
Yeah.
to our North Carolina seagrasses. And it's happened other places. And it's actually, fresher waters, it's happened here already. So this is Lake Matapesquite, just north of here. And this is like
Ooh.
home to 300,000 overwintering waterfowl every year. They used to feed on seagrasses or submerged aquatic vegetation in the lake all winter. And now, so in 2013, this eastern side of the lake was about 90% covered with seagrass. And in 1 year, 2014, between 2013 and 2014, something happened. And now, this is chlorophyll, so this is how much phytoplankton are there. Prior to this switch, chlorophyll might have been 20 or 30 micrograms per liter, which is actually fairly high. But now it's up to 200. And now actually this is old. I've been out there working over the last couple of years, and it averages probably about 150. And it's all cyanobacteria, so it's not necessarily like good algae either. It's not as toxic. Yeah, so this has happened here in North Carolina, and also up in Albemarle Sound. This is just south of Edenton. Edenton would be out here. Chowan River would be up here. There was a big patch of submerged aquatic vegetation on this north shore, and I can't remember why these surveys were done, but they were done in 2015, and there was this big seagrass patch, or SAB patch. About 2015 is when we started having really big cyanobacteria blooms up in this region, and in 2019, the whole patch was gone. So it's happened there as well. So, this is getting into the what are we doing about it part. We've been worried about our SAB in North Carolina now for a while. Things don't seem to be going in the direction they should. NCDMF has what they call the Coastal Habitat Protection Plan, which is a guide to protect and restore coastal habitats. So in their 2021 amendment to this plan, they specifically had a plan to protect SAB. So it starts as setting SAB acre goals, which is basically we want to get back to what we had in 2007. To do that, it's really focused on the idea that all this is driven by eutrophication. So it's setting this chlorophyll target. But first they had to decide how much light do we actually need. And to do that, there was a literature search done primarily using studies from Chesapeake Bay. How much light do the different seagrass species need? And then they went and looked at, okay, this is how much light they need, but if we're going to relate this somehow to a clarity, then we need to know at what depth do we expect seagrasses to exist. Because clarity is one thing, but clarity plus depth can tell you how much light actually hits the bottom. So they also used literature values, but local literature values for where seagrass is known to occur. And then this is the part where I finally come in on this, is an optical model that will relate chlorophyll, the suspended sediments, and the colors of organic matter to give you light to the bottom. So I worked on this model for a while to be able to set targets, like, okay, how high can chlorophyll be and still get light to the bottom to support seagrasses, or how much suspended sediment can we have? Those are the two things we can actually do something about. We can possibly do something about suspended sediments, and we can reduce nutrient loads to reduce how much phytoplankton is in the water. The color dissolved organic matter, I don't know how we manage that. And it's natural, it comes from swamps. The last thing we want to do is, okay, no more wetlands. Yeah, so this whole flow really initially was geared about eutrophication. So once we figure out how much chlorophyll we can have, then we set nutrient reduction targets, and then we're going to figure out how to actually make that happen in the watershed. I'd say at this point we're kind of here. We're still in this part. So the first part was trying to set the targets for clarity. So that involved knowing how deep we think the seagrasses or the SAB should be and what the light requirements are. So this literature review showed that the seagrasses living in the salty parts out here, the yellow areas, they need about 22% of incident irradiance, and 1.7 meters was how deep they've been shown to grow to. So if you do the math using the exponential decay function for light, shaped like that, you can come up with the coefficient that describes how steep light decays, and you can come up with the actual number for a clarity standard, and it would be 0.89 per meter. And you can do the same thing for low salinity, and 1.36. This is the number that goes into the model that I can then say, okay, I can get to 0.89 with this much chlorophyll and this much turbidity and this much sea bottom. And then this has actually been now proposed as a water body standard for the state of North Carolina. This clarity standard happens. So, yeah, this raised all kinds of questions though. I mean, when this came up, we're proposing a standard, it raised a lot of questions because we never measured this hardly in North Carolina's waters. The only places that have been measured, where a part has been measured is here in the Neuse River and here as part of MODMON, the Neuse River Modeling and Monitoring Program that Hans Pearl has been running since '94, and I recently took over when he retired. We just really didn't have any kind of data on this light attenuation coefficient to say, okay, if this is the standard, how are we currently doing compared to this, what's going to be a new standard? Yeah, so a bunch of different groups got together, including me at IMS and UNC Wilmington, and we partnered with the Cape Lookout National Seashore and APNEP again. And the goals of this were to assess the current clarity compared to this new standard, see where we're at, and then to understand, to use this optical model to understand the contributions of the three different things, the phytoplankton, sediments, and sea bottom. And then determine levels of chlorophyll and suspended sediments that will meet the light levels needed for seagrass. So the first thing we did was we looked, I say we in this sense, but this was really pretty much just me, looking at existing clarity data. Even though we didn't have a lot of actual measurements of light attenuation, we had a lot of these. This is a Secchi disc. A Secchi disc.
Okay.
Yeah. It's an Italian limnologist back in like the 1700s developed this idea. You lower this down, when it disappears, you can't see it anymore, you record how deep it is on the rope. These are half-meter increments. So,
No.
yeah. And it's easy. I mean, so this is like the low-tech way to measure clarity. It's completely comparable between water bodies, but it's not light attenuation. you can estimate light attenuation from it, but it's not light attenuation. To get light attenuation, you use an instrument something like this. So the little sensor there actually measures the light that's coming in, and then you would read it out on, and again, there's marks for half a meter, you lower it down, lots of different measurements, and you can work out how steep the light is attenuated throughout the water column. Yeah. So we looked at a long record of this type of estimates of light attenuation based on these measurements, and then we started measuring light attenuation in these different areas using actual light instruments. So these are the estimates. Yeah, I'll get here in a second.
Mhm.
Just look at the colors for a minute though. If you look at the colors, if you squint your eyes, all you're gonna see is yellow and reds. These colors, so these are the estimates of light attenuation, almost solely based on regressions of Secchi disk depth on the actual light, on the few measurements of light attenuation we had. The colors indicate the fraction of the observations that were made compared to that light level that we say the seagrasses need, or the clarity that we say they need. So this means that the light levels at that target depth are 25, so the target depth for the low salinity was 1.5 meters, for the high salinity was 1.7 meters. The light at those depths is a quarter of what we think there should be for this SAB to be healthy. And if you squint your eyes, what you'll see is a lot of not so good. I mean, we're a lot of like the 50 to 100%. And then this area, we're in that like less than a quarter of the light we think the SAB would need to survive at a 1.5 meter depth. There's some bright spots though. If you look at Core Sound, lots of greens and some blues. I mean, it's really, Core Sound's got the best water quality in the North Carolina estuaries. For sure. We don't have, if you look at the map, there's big rivers that go into it, so it's not terribly surprising. But it is the truth. I mean, Core Sound is the best water quality. And it shows up here. Yeah. So the measurements we made, we have a lot less data. You're going to see a few box plots. These box plots, these yellow lines are median values, so just it's like an average. And then on each one of these, this line would represent that standard clarity. So anything above it means that the light attenuation is too steep and the seagrasses aren't going to get what they need. Anything below it means they're good. So this is up in the Albemarle Sound area. About the only places where the water clarity is good enough is out here in the middle of Albemarle Sound. All these other places, yeah, it's just not. I will say, well, I'll show you that. I'll say it. I won't say that. And then for the Neuse and Pamlico rivers, the upper parts are just there's way too much light attenuation. But the lower parts, it's good. I mean, in the lower parts, it's meeting the proposed standard. Now I'll say it. Those areas in Albemarle Sound, they have tons of sea dump. Pasquotank River, I don't know if y'all have ever been there, but it drains, the water that drains in the Pasquotank River comes from the Great Dismal Swamp, and it looks like coffee. And if you had zero chlorophyll and zero turbidity there, the optical model says you still would never meet this standard because the sea dump levels are so high. And a lot of our waters, the upper parts of our rivers are like that. Even like the Trent River, for example, it would fail this new standard, but it doesn't have excessive turbidity or suspended sediments or phytoplankton. It's just black water. But on average, a lot of our water bodies look something like this, where phytoplankton and the suspended sediments and the sea dump contribute approximately equally. So it becomes an issue because we can't do anything about this, and yet it's an important contributor in our low salinity waters to light attenuation. In our high salinity waters, it becomes less important because there's the rivers are what's delivering the CDOM. Yeah. And then just one other thing that came out of this, looking at the long-term data from the news, it's real clear that there's signals in the water clarity that are associated with river flow. I mean, here, if you looked here, you could kind of imagine this like really clear water here, and then increasing and decreasing. It just, I haven't done any statistics on this to see it, but to me, it just looks like there are some long-term patterns that are primarily being driven by river flow. And this is all the way down here near the Minnesota ferry crossing. The further you get up, the stronger this pattern resembles the river flow pattern. And it makes sense. I mean, the river's delivering sediments, the river's delivering CDOM, and the river's delivering nutrients that fuels phytoplankton production too. So everything that should attenuate light is being delivered by reduced river flow. So the last thing we did with this model was start to try to get the question of what kind of chlorophyll and turbidity targets we could have and meet this new proposed standard. Got this kind of graphed out as a conceptual diagram. This red line here would represent the light attenuation of the standard. And then you can get there lots of different ways with lots of different combinations of turbidity and chlorophyll that you can manage. So you can slide it up or down here, side to side, on a background of CDOM levels that can either, if it's really high CDOM, then you have to have, it brings it this way, and you have to have really low turbidity and really low chlorophyll to get there. Yeah. So there's lots of different ways you can do it to get there, but after playing this model for a while, it looks like for low salinities areas, we would have to have chlorophyll of around 10 micrograms per liter of chlorophyll and turbidity around 3 NTUs to consistently get to water clarity we want. And then for the high salinity areas, because there's a lot less CDOM, we can have 15 micrograms per liter chlorophyll and 5 turbidity. Important point though, I mean those numbers, they mean something to me, they don't necessarily probably mean something as much to y'all, but the current standards are 40 for chlorophyll and 25 for turbidity. So well above. Our standards are really, they were designed for use in reservoirs, in rivers. They really weren't designed to protect water clarity for seagrasses. So this is kind of where we're at now, and there's lots of different conversations going on amongst the scientists and the policy makers to try to figure out how to use all this information to push forth the best standard. Yeah, so take-home messages that I hope you all got. The seagrasses are super important, and they're also just really cool. If you get a chance to go out and snorkel on seagrass, you should. They face lots of different threats, and it doesn't look like they're doing well. So there is a reason to worry, but there are lots of people around the state that are trying hard to figure out what the problems are and how to create policies and management strategies to deal with them so that we can still have our seagrass beds for the future. Yeah.
So you create standards, but then how do you achieve those standards?
The Clean Water Act's a mess. So the standards, once the standard is adopted, then the state will monitor. And if they monitor and the water quality is not meeting that standard, then that particular body of water will go on the EPA's 303D list. And that says that there has to be a TMDL, total maximum daily load, for something. If it's suspended sediments, it's a problem, then it would be suspended sediments. If it's phytoplankton, then it would probably be nutrients. And so there would have to be, that total maximum daily load would have to be designed. Now, my understanding is that plan, that's where they say, okay, we planned it, we're done. So the implementation of the TMDLs is the part that I still don't understand the teeth behind forcing the state to implement. And it could just be my ignorance, but I've asked lots of times.
So,
And I still haven't gotten any other answer other than mandates the plan. Yeah.
I would agree. I would say that the one caveat to that is that once you're put on the 303D list, that there's more resources that get put into that water
Yeah.
system. So you are at the top of the list for being able to apply for grants that will fund projects that will take you off of that list. But yeah, the theory of it being enforced is still up for debate, I think.
Yeah, there's like non-point source pollution grants that you can get, but they're, to be honest, they're small.
Yeah.
I mean, and so like if you're talking about a big watershed, like Albemarle Sound, for example, that covers 2 states, something like 7,000 square kilometers of, I mean, it's huge. I don't know, it is daunting.
how much of the pollution is a natural occurring as opposed to something that we're creating and causing?
Okay, let's just take the Neuse, pick on the Neuse River for a minute. Neuse River has been cleaned up pretty well. Back 25 years ago, the nitrate concentrations coming down the river were about twice what they are now. They're still at just above New Bern. They're probably in the 0.5 to 1 milligram per liter of nitrate coming down the river. A natural concentration might be 0.1. So that just gives you an idea of like how much is not natural. And it's coming from different areas. The real cleanups have been wastewater treatment, from the Neuse.
Farming?
Well, yeah, no, I was just getting that. In agriculture, there's been a lot of best management practices put in place for agriculture as well. It's easy to demonstrate the wastewater treatment success because they can actually measure what's coming out their pipes. And you can see that reflected in the nutrient data. It's hard to see the results from the best management practices. At the same time that all these best management practices have been put in place for agriculture, the population in the watershed of the Neuse River has doubled. So there's been a lot more development too. So it's,
How does the grass reproduce?
it depends on the species. That's a good question. The Zoster marina produces seeds. And my understanding is it does not, so it comes in the fall. It's when it sprouts and grows like crazy, and it grows like pretty good through May or June, and then it starts to senesce and die off during the summer. It doesn't make it through the summer, so it has to come back every year from seed. And then the southern species, the Haliduli, it reproduces just by spreading by its roots or getting like ripped up and a little fragment comes and takes root somewhere else. It doesn't have seeds here.
And does embedding oysters in the area help cleanliness of water, clarity?
Oysters do clear water. I know.
That's complex, but like clams, if you could get a load of clams back into seagrass, there's probably more data that suggests that would be good for local, wherever the nutrients are sitting.
You can't get permitted to put oysters in a place near seagrass.
Yeah, it's true.
Because
Well, because the folks who made that decision think that they're in competition with each other, when in fact, they support each other. Both the oysters and the seagrasses grow better when they're within 6 to 12 inches of each other.
Yeah.
There's been some projects around, like, I think like Harper's Island and stuff with like planting. Is it like kind of restoration of seagrass? And I know those are just in, I don't know if those are just in recent years, but has there been any kind of, I guess, impact that's been kind of, I guess like the study of like kind of some of the longer term or shorter term or longer term impact of the restoration efforts? Or, you know.
Joel's.
I mean, I came here because I wanted to hear about this light bioptic model. That's
Oh,
why.
yeah, sorry. I was just curious about.
I don't want to seem like I'm a big mouth, but
I don't know anything. about
so
this.
restoration in the water in general is just hard. Gosh, it's hard. Like the lab that Nate's at, they've restored like 150 oyster reefs around the Middle Marsh area. And man, they look good for like 10, 20 years. Like everyone's like, hey, this works. And then after Florence, like half of them just fell apart. And seagrass is probably the harder. So I guess if I was going to tell a good story, so it starts with a bad story. In the 1930s, the Delmarva Peninsula has bays that are similar to some of ours, except it's cooler. And they had both hurricanes and wasting disease. And they lost all their grass. All. And then in the late 90s, a guy at the Virginia Institute of Marine Sciences and his colleagues, they just started dumping seeds in it. Dumping seeds for 7 years and nothing. And then like the 8th year, all of a sudden the grass took off. And so they planted 600 acres, and I think they have, or it might be hectares. Can't remember if it's acres or hectares. And like Nate said, like do the 2.2 multiplication or division. But they did hundreds of something, and now they got 6,000. So the grass at a certain point it took off. And we're similar and different in that our water quality seems to be pretty good. Would you say that we have lots of places that light is reaching the bottom?
Sure, that don't have seagrass.
They don't have seagrass.
Sure, absolutely.
And so we have been collecting in a meter square of eelgrass, and the museum is our partner in doing this. In a meter square of seagrass, the eelgrass can produce like thousands of seeds. Thousands. Well, you're only going to grow 15 to 20 plants in that space. So we think there's a lot of excess seeds. Why do plants do that? Don't know. It might be for the hurricane years. But we've been out with volunteers and we've been harvesting seeds. And like this year we harvested 2.5 million seeds. And now we're going to try to plant 25 seeds per meter squared, and that allows you to do about 25 acres of restoration. So here's what we're good at. We're good at pulling the seeds, and we're good at holding the seeds. We're not very good at planting the seeds and getting those to germinate. We get like this very light fuzz. We get a little fuzz of grass. And we've got to get to the point where we get like a meadow to pop up. And based on the Virginia model, we think if we could get to the point of a meadow popping up, then it sells seeds. But we can't get beyond the fuzzy stage.
Like ocean pollinators or, sorry,
Generally,
I'm
there's
very
thought to be
ignorant,
very few ocean pollinators.
Okay.
But